Welcome to the presentation of our work, Event-Based PD Controller Fully Realized in Neuromorphic Hardware, a 1DoF study. I'm Rasmus from University of Southern Denmark, and this is work done in collaboration with Antonio and Alpha from Institute of Neuroinformatics in Zurich, Lian and Anders from the University of Southern Denmark, and Julia with Intel Neuromorphic Computing Labs in Munich. Artificial neural networks are widely used in robotics, especially in computer vision but also in closed-loop control. Using large artificial neural networks comes with the need of a large amount of processing power. Spiking neural networks, on the other hand, are a type of artificial neurons much closer to the biological neurons. They accumulate input current and set out a spike whenever their internal variable, the membrane potential, reaches the threshold. Specialized hardware has been developed to simulate such spiking neurons with the goal of low latency and low power usage, while being able to scale to millions of neurons. Many of you will already know about artificial neural networks. The neurons are modeled based on a very simplified version of the neurons in the biological brain. The artificial neuron summarizes the weighted inputs and outputs a value calculated by a time-independent transfer function of the summarized inputs. This means an artificial neuron will always have the same output each time it's presented the same inputs. While artificial neurons have no mean of time and therefore no memory, spiking neurons heavily rely on memory and time. A spiking neuron integrates the input current over time until a voltage threshold is reached. At this time, the neuron will send a spike through the connections called synapses to a postsynaptic neuron. The voltage potential of each neuron is calculated at each time step, which uses a lot of power when simulated on CPUs or GPUs. But few hardware accelerators have been developed to optimize speed and decrease latency and power usage. One of these are Intel's neuromorphic research chip Loihi. Attempts have already been made towards adaptive on-chip SNN-based motor control. For instance, in this work done on University of Waterloo, where an SNN was used to control a robotic arm. Earlier this year, we have shown our first version of a SNN-based PID controller. Now we have improved the integrational precision as well as improving the closed-loop response time. Furthermore, we have measured the power consumption of the Loihi chip in progress. We used a Loihi chip to simulate the spiking neural network to perform closed-loop control of a drone constrained to 1DoF, which only enabled it to rotate around the horizontal axis. The drone was connected to a small single-board computer which hosts communication interface for sensors and actuators, as well as the Loihi chip. The Loihi chip consists of 128 neuronal processing cores, which in total can simulate up to 130,000 neurons. Furthermore, the Loihi chip features 3 microprocessors used for synaptic learning, spike input-output, and monitoring. In this work, we simulated our spiking neural network on a Cabot Bay. The Cabot Bay system features 2 Loihi chips, but we only used one of them. We used the USB interface in order to reduce the development time of the system, but in order to increase the communication speed and therefore the speed of the closed-loop response time, a low-level interface could have been used. The classical PID controller is a simple controller and fits for most closed-loop control tasks of dynamical systems. For drone control, the PID controller calculates the error signal E by subtracting the current angle of the drone Y from the desired angle of the drone R and outputs the motor velocity for the drone. This can be achieved with 5 arithmetic operations: calculating the error signal, calculation of the integral, calculation of the derivative, applying PID gains, and summate the signals. In order to perform these operations, we use space coding in combination with the simple tricks as explained in the following slides. First, we need to represent our values in some way. In a spiking neural network, signals can be represented in many different ways, including rate coding, where a value is represented by the firing rate of a neuron, or temporal coding, where a signal is represented by the timing of each spike. In this work, we only use space coding, where each neuron is represented as its own value. This way, we limit ourselves to use low-resolution discrete values, but with the advantage of having a deterministic system. For each time step in the simulation, a new sensor input arrives and is linearly mapped from degrees to a neuron index. The corresponding neuron then fires the very next time step. This way we restrict the input populations R and Y to produce exactly one spike at each time step, which enable us to use a 2D arithmetic of population that we presented earlier this year at ISS. Each neuron in the 2D population works as a coincidence detector, meaning that it will only spike if it receives two spikes simultaneously. The output of these neurons is mapped into the E population in a way that E represents the result of R minus Y. This results in a behavior where exactly one neuron in the 2D population spikes each time step, and therefore also exactly one neuron in the error population. The delay of each synapse is one time step, which means the propagation delay from the input to the output is 2 time steps. The integration pathway then integrates the error signal using a positive integrator neuron, C+, and a negative integrator neuron, C-, which integrate the neuron index of the active neuron throughout time. When the activity of the E population is positive, it excites the C+ neuron and inhibits the C- neuron, and likewise for negative activity of the E, where it excites the C- neuron and inhibits the C+ neuron. When the C+ or C- neurons have been excited for a while, they will reach a threshold which will make them fire a spike. A spike from C+ or C- will activate a neuron in the shift up and shift down population respectively. The activity in the shift layers will move the activity of the I population like seen in the slide. When C+ fires, it will excite all the neurons in the shift up population, but only one neuron will also be excited by the I population and therefore be excited enough to be activated. The activation of the neuron in the shift up population will result in inhibition of the corresponding neuron in the I population and the excitation of the neuron above it. For the derivative, we simply delay the error signal one time step and subtract it from the current error signal, the same way we calculate the error signal based on R and Y. We then have our P, I, and D signals all ready to be weighted and summarized. To apply gains to the P, I, and D signals and combine them to one output signal, we split each population into a positive part and a negative part. The index of the active neuron in the P, I, and D population determines how many neurons should be firing in the corresponding plus and minus populations. For instance, in the D population, the neuron with index 0 is active, which means no neurons in D plus or D minus should be activated. In the I population, the neuron with the index 2 is active, which means that 2 neurons in I plus will be activated. In the P population, the neuron with index -1 is active, which means that 1 neuron in the P- population will be activated. These populations are then connected to population B using the weights Kp, Ki, and Kd from the respective populations. The threshold of the neurons in population B is proportional with the neuron index. This means that the more excitation put to population B, the more neurons in the population will fire. Each active neuron in the population will then inhibit all the neurons of population U with the lower indices and excite the neuron with the same index. This ensures that exactly one output spike is present at each time step. The index of the active neuron is then linearly mapped to the motor commands to the drone. While all these figures show population size of 5 neurons for the input populations R and Y as well as the output population U, we implemented using 63 neurons in each population. This also increases the size of all populations within between. We ran the setup for 10 trials while recording the target angular position of the drone and the current angular position of the drone. We did the same for a CPU-based PID controller, which we implemented using a numerical precision of 6 bits, which is equivalent to population sizes of 63 neurons. The red trace shows the angular position and thereby the control performance of our SNN-based PID controller, while it presented the target angular position shown in blue. And the green trace shows the performance of the controller programmed on CPU. We benchmarked the controllers using overshoot, the rise time and the settling time, averaging over 10 runs for each controller. Furthermore, we measured the power consumption of the Loihi chip while running the SNN PID architecture. We tested with different numbers of controllers running in parallel to observe how it scales. The results show tests with 1, 3, 6, and 15 controllers, which together indicates that it scales linearly as expected. In this work, we propose a new way of implementing a PID controller in a spiking neural network for robotic control. We tested it on Intel's Neuromorphic research chip, Loihi, and used it to control a 1DoF drone. The controller was benchmarked against a CPU-based PID with the same numerical precision, which shows comparable results. Furthermore, we measured the power consumption of the spiking neural network running on the Neuromorphic research chip Loihi. The next step would be to apply on-chip learning for the synaptic weights represented by the PID gains. This would make the drone tune the PID gains itself, as well as adapt to external disturbances such as added weight or malfunctioning actuator in case of a redundant rotor setup. Furthermore, event-based neuromorphic hardware is ideal for processing event-based sensory input, such as from an event-based camera. Therefore, we aim to further explore this field.